Now I'll provide the two proofs, starting with the one for the cosmic microwave background radiation. We are going to see later that this is the final formula for finding the Hubble constant from first principles for non-compounding, non-relativistic equations. In this formula, if the middle term were to be very close to 1 and was significantly smaller than this final term, then this formula could be reduced to that. And as we've seen before, this is the formula for the cosmological redshift equation in the non-compounding version. So this term is equal to the velocity of the phantom object over c, which gives us this, that the redshift equals Vp over c. And so that, since that is a derivation of the Hubble equation from first principles, that shows us that h from first principles equals h from calculated using the cosmic redshift approach if our initial condition is met, which is that this middle term is very close to 1 and is relatively small when compared to this last term. And now let's see why that's true for the cosmic microwave background radiation. Well, the first thing we note is that the speed of light is 300,000 kilometers per second. So this middle term will be very close to 1 for any value d1 that's at the small end of the range. The second thing we note is that if the universe is about 13 to 14 billion years, the cosmic microwave background radiation has been traveling a long time before we observe it on Earth. So let's just say it's been traveling for about 12 billion years. I'm just picking a number for illustrative purposes. Now 1 megaparsec equals 3.2 million light years. So if you divide the length of time it's been traveling by this, 12 billion divided by 3.2 million, we find the distance for L, or the dl, would be in the range of 3,000 to 4,000 megaparsecs. And that would be the value of dl that would go here in the equation. So we can see that for any small d1 measured in megaparsecs near the time of the Big Bang, when the cosmic microwave background radiation was emitted, then both of these conditions are met. This would be very small and close to 1, and this would be very small relative to this, which allows us to treat this as being equal to 1 and create this approximation, which gives us the near equality. And now I will explain why for almost all other observed galaxies or other objects for calculating the Hubble constant, the value for the Hubble constant calculated from first principles will tend to be near 1/2 of the value calculated from using the cosmological redshift approach. You're going to see, if you haven't already, that this is the final non-compounding formula for finding the Hubble constant using the first principles formula. You're also going to see, or you've seen, that d1 equals dl over 1 plus y, where y is defined, and you can find that on the toolkit. So if we substitute that in for d1, this term becomes this. Then if we multiply the bottom by c over this, and then do the same on the top, the middle term becomes this. So this equation becomes this equation. Now, when we multiply this out, it leads to this equation, where the final term I've just written in x as representing all of this stuff times that. And we note that this final term is that x over c squared, which means that it's a very small number, and so we can disregard it since it's so small. And when we look at what's left, we can see that if y is very small, then this will evaluate down to very close to being c over c, which is 1. And so this will be 1 plus 1 equals 2, giving us this equation, where the ratio of the wavelengths equals 1 plus 2 dl over c. dl times h over c. Now, you may have noticed that here I switched from referring to h1 and hb down to here just referring to h. And that transition is explained in the more detailed video regarding solving the h first principles equation. In any event, as we've seen, this equation can be converted quite simply into this. The observed redshift equals 2 dl times h over c. And we can contrast that with the result of the cosmologic redshift formula, which will give us this formula, that the observed redshift equals dl times h over c. So since the observed redshifts are the same and dl and c are the same, you can easily see that this formula will be giving us a value of h that's 1/2 of the value that will be given to us by this formula. So the key question is, how do we evaluate this number, which is the weighting factor for dl h1? And we can see some examples of how to do it down here. You'll see in other segments, and you can see it in the toolkit, that y equals 1/2 dl hb over c. So if we take some representative examples of dl, 100 megaparsecs, 400 megaparsecs, and 1000 megaparsecs, and if we take two representative values for h equals 72 and h equals 36, using this formula for y and this formula for the complete weighting factor, we can simply calculate what the weighting factor is at these distances dl for these distances, or for these amounts of the Hubble constant. And you can see the results on this table. For everything up to 400 megaparsecs, the weighting factor is 0.954 up to 0.977, depending on the value of h. Even at 1000 megaparsecs for dl, the weighting factor is still 0.893 to 0.943. So you can see that I was actually being quite generous up here by writing this end of the range as being 1 over 1.8. It would have been a lot more accurate to write 1 over 1.89, which is the weighting factor for distances up to 1000 megaparsecs. with an H of 72.